All right, so for these physical applications, I'm going to do something a little different. I'm just going to go through a couple applications separately in different videos. That way we can keep them short and keep them kind of on target. So for this video, our goal is that we want to find the mass of a one-dimensional object, but really we'll have it be a three-dimensional object that's thin enough that it doesn't really matter, given some information about density. This is a classic physics engineering problem that isn't so big of a deal if we have a fixed density. So with fixed density, we know that density in general is the mass per unit of volume. So for an object with a fixed or uniform density, same across the whole object, density is literally just whatever the mass is divided by the volume. And you'll notice that we can solve for mass by just multiplying both sides by volume. So if we know the density of the object and we know how much of it there is, we can multiply those two things together, and there we go, we have the mass of the object. For us, though, what we're going to do is we're going to talk about the mass of an object with variable density. So we're going to consider some kind of a thin bar. It's going to be thin, so the three dimensions can essentially reduce down to one dimension. And it's going to have variable density. I'm trying to represent that with this kind of gradient coloring. So we'll say on this end, very dense, and on this end, not that dense. But all we really care is that the density changes throughout here. What we can do is use this slice and sum method that we've done. We could cut this thing up into all these little subintervals. And I know I'm not doing this using a regular partition, but whatever. And then what we could do is we could pick some sort of a point in this subinterval and find the density here to represent the density of the whole subinterval. And then we could go ahead and say, all right, assume there's a uniform density on this subinterval, multiply the density by the volume, done. So for us, when we multiply by volume, since we're reducing this down to one dimension, we're really going to just multiply by delta x. So we can think volume is really going to take place of this kind of like size dimension, and now that we're in, or size variable. So now that we're in one dimension, we'll say size is really just going to be like a length here. Maybe I'll actually write out the rest. Okay, so we're going to assume that we have some density. We'll pick some x sub k star, and we'll say that the mass on each subinterval, m sub k, is going to be exactly a density function. We'll use rho for this, the Greek letter. Evaluated at x sub k star times delta x. There's our mass times our distance, our density times our distance. And then we can say our overall mass is approximated by the sum of all of these. So again, we're adding up the mass on each subinterval, and then we could say once we apply a limit to this thing, as n goes to infinity. Oh, my n's got a really long tail here. We have not necessarily a finite number of these, but an infinite number of these little subsections where we multiply the density by the width, and that turns into an integral from a, this point, up to b, this point, of just our variable density function. That looks like a p, but I want it to be a rho. There we go. dx. So here's our integral formula. So for the mass of a thin wire, we'll call it, and it can be a thin anything, but we'll assume a thin wire. So we'll suppose a thin wire is stretched across the interval from a to b, and it has a density of rho of x. The mass of the object then is this integral formula that we just did. So here's a quick little example. Let's consider a very thin wire that is 3 meters long. So I'm going to convert this to centimeters because that's what we're using for this density. We'll say 300 centimeters then. And it's got this density of 3 grams per cubic centimeter on one end and 8 grams per cubic centimeter on the other. We're going to reduce this down to one dimension, and so we're going to pretend that it's actually 8 grams per centimeter and 3 grams per centimeter here. Again, this is a bad assumption, but if it's very, very thin, that's okay for us to do. And what we're going to do is assume the density changes linearly. So what we need to do is try and figure out what the density function is. Well, if it changes linearly, then our density function is going to be this kind of mx plus b type of situation. But what I'm going to do is say we have 2 points, right? We have a point at 0 with our density being 3, and we have a point at 8 with our at 300 at the end of our wire with our density being 8. And so what we can do is find a slope, and then there's our y-intercept. Our slope is going to be a change of 5 over 300, and our y-intercept is 3. 5 over 300 is really 1 over 60. So this is x over 60 plus 3. That's our density function. Now what we can do is we can set up our mass by integrating on this interval. We'll say one end is 0, the other end is 300, because we started at 0 and went to 300 centimeters. And we have this nice density function, x over 60 plus 3 dx. This is an easy one to do. X squared over 2 is our antiderivative, but then we're dividing by 60 as well. So this is x squared over 120 plus 3x, and we will evaluate this from 0 to 300. Evaluating at 0 is really easy. It's just 0. So let's go ahead and square 300. What's that? 9 with 4 zeros. So 90,000 over 120 plus 3 times 300, that's 900. I don't know what 90,000 over 120 is. Let me grab a calculator and see. All right, so we're at 90,000 over 120. Whoops. That's 750. All right, I can do this math then. 750 plus 900 is 1650, and we're at grams for our units. Again, not too big of a deal. We had to know that the density was changing linearly for us to be able to find this density function, so maybe we'll get some information about how our density is changing and enough points that we can build a function that'll do it. Or maybe we'll just be given a density function. Once we have a density function, though, and we know how density changes, we can integrate that across an interval to find the mass of an object, which works out pretty well.